Now remember, any hypothesis test starts the same way. H0, H1, and H0 is always that something equals something. It's always an equals. Now H0, so what do we got? A wildlife reserve monitors the number of rare bird sightings. We think 3.2 per week. So we recorded some over a 4-week period. We want to see if there's evidence of a change. Ooh, a change. Ooh, a change for week. All right. Now, we are looking at the mean of a Poisson, all right, because it's average number of sightings. Now, we do have two options here. The question has given me my default in terms of sightings per week. So you could list it as 3.2 per week. Or we could immediately scale that up for the 4-week period, which is 12.8. These mark schemes will, actually, let's use different colors. And I'll show you where we change things for that, but you are allowed both. Now, like with any hypothesis test, the numbers don't change between H1 and H0. The only thing that changes is the sign in between them. Now we want a change, so that's going to be not equal. So we're on a two-tailed test. Now the key thing to go with this is tell me what lambda is. If you're doing a hypothesis test for the mean of a normal, you tell me what mu is. If you're doing it for P of a binomial or a geometric, you tell me what P is. If you are testing the mean of a Poisson distribution, you tell me, if you're using lambda, what lambda is. So lambda is the mean sightings per and either, oh, that was interesting, week if you've gone for 3.2, or if you decided to scale it up, you will tell someone that you've scaled it up to 4 weeks. So that's the thing, Brandon. So if we go what Path has done, using lambda is 12.8 in H0, we will say that lambda is the mean number of sightings per 4 weeks. All right, so it doesn't matter which one, and if you go look at any of the mark schemes, they will give options for both. Now, in terms of our calculations, we're going to say, well, X is number of rare bird sightings in that 4-week period. Here we don't have a choice. Why? Because our test statistic will be in that 4-week period, and we want the critical region in a 4-week period. So here we don't have a choice. So that 12.8 will be coming in here somewhere. Now, a Poisson distribution tends to look something like this. It's got some skew to it. We want the critical region for a 5% level of significance. All right. Now, remember, two-tailed test, that means we are trying to find here at 2.5%, and we want the upper tail at 2.5%. Now, this is where we're going to go use our distribution mode, and this is where really it comes into its own, but I'll do them using both. This is a discrete distribution, so we're not going to get exactly 2.5% in both. Right, let's find the bottom tail. So less than or equal to, our lambda is 12.8. Now we just need to take a punt. I don't know, let's go with 3. 3's in there. So that is 1 point. So that's 0.9. So what we're going to do is, what you can do in here is you can actually modify the x value there, but you can also modify the probability that you want. So 0.025. And in fact, it says here, so if we read this, the probability that x is less than or equal to 6 is 0.029. It's rounded it up. So we're actually going to go look at 5 instead. And there we go. So in fact, we're going to say that my critical value at the bottom is x less than or equal to 5. And that gives me a probability of 0.0122. All right, if we'd gone to 6, we're a little bit too big. In fact, 6 is bigger than the other one, but there we go. We want to be fully in it. And then we can go look at the top end. Oh, yeah, I mean, sure. So 20 is a little bit too big. So 20 is going to be a little bit too big. So let's look at 21 then. And there we go. So if I look at 21, the probability that x is bigger than or equal to 21 is 0.0216. Okay, so those are my two tails. So 5 will be firmly inside here. Right, 5 is somewhere like that. 5 is there, 6 is outside, and here 20 is there, and 21 is just inside. All right, so that's us using the distribution mode. You could do the same thing, but what I quite like about the distribution mode is you get that visualization of the distribution, and you can play around with the numbers directly here, which is quite cool. If you go up into your distribution mode, which will be very similar to the interface you get on the ClassWiz, you could go distribution, you could go Poisson, you can go inverse Poisson. Now the area is always the area to the left. Lambda here is 12.8, so let's see what it would give me for the upper one. It's suggesting 20, but you would have to go double check that 20 because it's actually outside. I can never remember for the life of me how the calculator rounds for discrete distribution, so you need to go double check. This is where having access to the nice pretty thing is really cool. All right, so if I got a value of 21 or higher or a value of 5 or higher, when I actually measure the number of sightings over a 4-week period, I would reject H naught. You just have to do a bit of trial and error, Anthony, I'm afraid. So you would have to go and just try a few. So we would go normal, we'd go Poisson, we'd go BCD. And you would have to do a bit of trial and error. So well, let's start with 3. That is too small. So we'd go to 4, we'd go to 5. Okay, that's less than 2.5%. Let's go to 6. That's more than 2.5%. So we've found it. Yeah, Mifazia has a point. You could go to the list function as well. So that's where you can go, well, let's try 1, let's try 2, let's try 3, let's try 4, let's try 5, let's try 6. So all the ones that you want to try, and then you can go distribution, Poisson, BCD, and that's where you can say, look, I want you to check, oh, it does lower and upper for me. You don't need to do that. I'm going to make that list 2. I'm going to make that list 1. And then I'm going to have to go do 0, 0, 0, 0, 0, 0. Because it wants a lower and upper bound. So my lower bound is list 2, my upper bound is list 1. And then you get all these probabilities, and you would see, oh, 5, oh, 6, and there we go. And you can see right away there. It's these sorts of things that having the big calculator is most useful. I won't fib. Right, now, what is a type 1 error? And I do have a slide on that right at the end where we'll talk about type 1 and type 2 errors. Might have to speed up a little bit, actually. So a type 1 error is basically your significance level, all right? It's essentially your significance level, but the real one. All right, so in our case here, we will reject if we're less than or equal to 5 or bigger than or equal to 21. So in our case here, the probability of a type 1 error will be the actual area in my two tails. So it would be 0.0122 plus 0.0216. Now that's not what this thing is asking me to answer, by the way, 338. But that's just FYI. But what it is that is the probability of incorrectly, actually, why am I doing that there? So it is the probability of incorrectly rejecting H0. Now let's have a talk about that for just a second. Because remember, what a hypothesis test is doing is we're going to say, look, let's assume that everything is kosher, right? Lambda is 3.2 or 12.8. Then we measure something. If something really unlikely happened, then my assumption is probably wobbly. Now, what do we define as something really unlikely? Well, in this case, either in the top 2.5% or in the bottom 2.5%. But being unlikely is not the same thing as being impossible, right? So in this case, you might see 22 birds, which on a probability scale is very unlikely, but it's not impossible. So you would look at 22 birds and go, oh, that's an abnormally large number of birds. No way is lambda 3.2. That was far too many birds, rare birds, for lambda to be 3.2. But in fact, there is a probability of you seeing abnormally large number of birds. It's 2%. Okay, so there is a chance of you making that mistake. So in our case here, but look, in the context, so it's the probability of concluding probability of incorrectly concluding that the average number of sightings, or that there has been a change in average number of sightings. That's a lot of words for a mathematician to write. But do be aware of this idea of context. All right, we need context. So put it in the context of this question. Okay, but that is the rough breakdown of how we're going to set up a hypothesis test for Poisson.